wheel of a gyroscope. This dependency exists in the basic parts on the miniature Mercury compass, has its exact counterpart on an actual compass, the Sperry Mark 14. The rotor is 10 inches in diameter, with nearly all of its 55 pounds concentrated in the rim. To turn it 6,000 times a minute, this rotor is not driven by an external force. It is actually the armature of a three-phase induction motor. The rotor bars and laminations are mounted on the inside of the rim, and the field windings are bolted to the interior of the rotor case. The rotor axle revolves in ball bearings which fit into the bearing housings of the case. As a unit, the rotor and case constitute a complete electric motor which corresponds to the model gyroscope rotor with the inside ring. This horizontal ring represents the Mark 14 case. On the sides, two horizontal studs support the case in the bearings which are held by the vertical ring. The rotor and case are located inside the vertical ring, just as in the model. Then the C-frame holds this assembly on the model, while on the Mark 14, the corresponding assembly is supported by a wire composed of 18 separate strands. This is the basic component of the gyro compass, and the first of our 5 major assemblies. Known as the sensitive element, it is simply a gyroscope rotor mounted so that it has the same necessary 3 degrees of freedom that are apparent in the model gyroscope. First, let's consider the spinning axis. The model gyroscope gets its power from force applied to a string. Since the compass is in itself an induction motor, its power comes from a 3-phase, 210-cycle, 50-volt current. Because of its weight, the rotor requires about 10 minutes to attain its speed of 6,000 revolutions a minute. As in the model gyroscope, the vertical ring provides the sensitive element with freedom of movement about the horizontal axis. The model is given freedom about the vertical axis by mounting it in a frame. On the Mark 14, vertical freedom is provided by the wire suspension. A pair of weights known as compensator weights are attached to the vertical ring so that the element is equally balanced in the north-south plane and in the east-west plane. Although the gyro compass has 150 times the directive force of the magnetic compass as it turns toward the meridian, it still would not be sufficient to overcome the friction of an ordinary support. Since even the finest ball bearings would offer too much resistance, a practically frictionless method of mounting is employed. To accomplish this, a phantom ring is provided to form the basic part of the second major assembly, the phantom element. Then the sensitive element is suspended within the phantom ring by the wire suspension, the top end of which is secured to the top of the phantom stem, as seen in this cutaway model. The third major assembly is the spider element. This element provides a support for the first 2 assemblies, the sensitive and phantom elements. The stem of the phantom fits inside a thrust bearing on the spider, and the compass card is fastened on top of the phantom. As the sensitive element turns in seeking north, it would tend to twist the wire suspension. Then the wire, trying to untwist itself, would introduce a precessional force that would keep the compass from turning toward the meridian. To prevent the wire suspension from becoming twisted, the phantom does just what its name suggests. It follows every minute movement of the sensitive element, so the wire has no chance to become twisted. But what makes it follow so exactly? No, it isn't magnetism, and it isn't black magic. The power to drive the phantom in its pursuit of the sensitive element is supplied by the azimuth motor, which is geared to the phantom. With every movement of the sensitive element in either direction, the motor starts and drives the phantom ring around into perfect alignment. As we have already seen, The compass card is an integral part of the phantom element. Therefore, when the sensitive element turns in its north-seeking movement, the azimuth motor drives the phantom and the card into position. In this way, the zero mark of the card always remains aligned with the north-seeking axle, and the 180-degree marker stays aligned with the south axle. Response of the phantom is very quick, and the sensitive element seldom gets more than 2/10 of 1 degree away from the pursuing phantom. These movements are greatly exaggerated so that we can follow them more easily. Now the question is, what controls the direction and speed of the azimuth motor? If the sensitive element turns one way, what prevents the motor from driving the phantom the other way? What keeps the motor from driving the phantom faster or slower than the movements of the sensitive element? The answer is the electronic follow-up system. It consists of an amplifier with 3 electronic tubes and a transformer with a movable core. The entire purpose of these 2 elements is to control the current to the azimuth motor so that it will run in the right direction for the proper length of time. The transformer is mounted on the phantom ring. It has an E-shaped soft iron core with a primary coil in the center and 2 secondary coils wound in opposite directions. The movable core, known as the armature, is nothing more than a bar of soft iron. It is fastened to the east side of the sensitive element. Now when the sensitive element is again back in its place inside the phantom ring, we can see how the transformer is fastened to the phantom ring and the armature is attached to the sensitive element, so that the 2 parts are positioned opposite each other. They are very close together, with one side detached so that it can move across the face of the transformer when the sensitive element moves. This movement of the armature transmits electrical impulses to operate the second part of the follow-up system, the amplifier. The amplifier, in turn, controls the power which operates the azimuth motor, its speed and direction. Since the armature is fastened to the sensitive element, it is really the sensitive element that controls the azimuth motor. Now let's trace the chain of events that take place in this follow-up system. Suppose the compass has been started off the meridian. The sensitive element is turning toward true north. It carries the armature along with it, offsetting the armature in relation to the transformer. This produces a signal which is amplified to control the current sent to turn the azimuth motor. The motor drives the azimuth gear, which is fastened solidly to the phantom element. This causes the phantom to follow every movement of the sensitive element. This, then, is the operation of the follow-up system. Because the phantom is constantly following the sensitive element in either direction, the wire suspension cannot become twisted. Therefore, the sensitive element is free to turn in its north-seeking movement, unrestrained in this almost frictionless support, while the azimuth motor keeps the phantom in exact alignment and the zero mark of the card right on the north axle. To complete the compass, there are 2 more major assemblies. The Mercury ballistic, our 4th major assembly, has 2 pairs of Mercury tanks, 1 pair on the east side and 1 pair on the west side. The tanks of each pair are connected by a tube of small diameter through which the mercury can freely flow as the ballistic is tilted about the horizontal studs. These studs fit into bearings on the phantom. At present, the ballistic is free to move about its axis, accomplishing nothing. In order to serve its purpose of causing the rotor to precess, it must be connected to the rotor case. This is accomplished by means of a connecting link which fits over the offset bearing on the bottom of the rotor case. Now, if one side of the ballistic is heavier, the force of gravity will try to tilt the rotor, causing it to precess, bringing into operation those principles which make the gyroscope a compass. This is the complete master compass, ready to be installed in the BINNACLE, the 5th major assembly. The spider has 2 trunnions which carry the entire weight of the master compass. These trunnions are supported in athwartship bearings in the gimbal ring, which in turn is mounted in fore and aft bearings inside the binnacle. This mounting permits the compass to remain upright regardless of the rolling and pitching of the ship.